Today we're going to clear up a topic that confuses many engineering students, and that is what exactly is the radius of gyration and why does it matter. Now I'm going to explain the idea in simple intuitive terms and then show you multiple worked examples so that the concept can become completely clear. Now imagine you have a shape or an object. Now that shape, it could be a disk, as I'm trying to draw here, or it could just be something irregular as you see over there. And you want to describe how its mass or how its area is distributed relative to an axis. Now let's say this represents my axis, and I'm just going to use X to label it. Now the full mass or area, it may be spread out in a complicated way. So for example, even this circular object here, we may have more of the mass concentrated at the edge there. And this other irregular shape, it's already complicated, so no need to make it even more complicated. So these are our two objects that we're focusing on. Now the radius of gyration, it lets you pretend that the entire mass or area is concentrated at one single distance from the axis. So say this is my axis, and this complicated circular shape, the radius of gyration lets you pretend as if it's that shape there that I've just drawn, and its distance from that axis is k. And the same thing for this other complicated shape over here. Now the distance k, that's called the radius of gyration. So the idea is if all the mass or area were concentrated at that fixed distance k, it should have the same moment of inertia as the real shape. So we're now gonna have to link the moment of inertia with the radius of gyration for you to get the complete picture of what we're dealing with here. So just as a quick reminder, the moment of inertia, it represents the resistance to change in motion. So that could be how difficult it is to stop something from rotating, or to start it, get it started to rotate, or change direction. Any of those resistance to change, that's what we're talking about here. And it's quite an important topic in engineering. So the moment of inertia for mass then, now that is I equals mr squared. And if we were to use radius of gyration, that would be I equals mk squared. And if we were to consider the radius of gyration for, let's say, area, then it would be very similar. Instead of having mk squared, it would just be area times that distance squared, so ak squared. So in both cases, we can see then where for mass, the radius of gyration, it's the square root. If we were to just rearrange this formula here, then radius of gyration for mass would just be the inertia divided by m. And if we were to look at the one for area that we just wrote, then it would be very similar. So it's just the square root of I over a, inertia divided by area. So depending on whether you're dealing with mass or area, that's what would determine which of these you would use to find the radius of gyration. Now let's use some examples and put it to practice so you can appreciate better exactly what the radius of gyration does. Now this should make the concept crystal clear. So let's say we have a uniform circular disc like this here, and we're saying that the mass is spread evenly in all directions, and it's just a plain solid disk. Now the formula for that, for inertia, would be I equals half mr squared. I'm sure you would have came across this formula before. But if we were to use the formula with radius of gyration, then it would be I equals mk squared. Now for this particular concept, remember that the radius of gyration, the main goal is if we were to find the inertia of this plane disk, if it starts to rotate, using this formula. Then whatever answer we get using this formula, I equals mr squared, we need to be able to get the same answer for inertia using the radius of gyration. So what that means is if we were to equate the two equations, so say we were to have the mk squared equals our half mr squared, then in this case, after we cancel out the m's and we're left with k squared, then k would be equal to, that's just half r squared, and we square root that, which if we were to simplify that, then the square root of r squared is just r, so we're left with r over root 2. And that would be how we find the radius of gyration for this here. So we're going to put some numbers in and you will see exactly how the radius of gyration works here now. So say we have a solid disk, just like the example we had previously, and its mass was say 12 kilo, and its actual radius, so that's the radius of the disk itself, is 0.4 meters. Now, if we were to use the actual formula to find inertia, where I equals half mr squared, then let's see what we get for this. So we would end up with half times by 12 times by 0.4 squared. And if you put that in your calculator, then you're going to get I as 0.96, and our unit mass, that's kilograms, and r squared, so kilograms meter squared. So let's use the formula we just had to find what the radius of gyration k would be. So that's r over root 2, and this is 0.4 divided by root 2, 1.414. So we get a k value here of 0.283 meters. So remember that the goal is to get the exact value that we had up top. So let's see if that's the case now. So if we have I equals mk squared, value of m, again, that's 12, multiplied by the k value, which is 0. This would give us 0.961, somewhere thereabouts, so we can just round it. So that's kilograms meter squared. And as you can see, using the radius of gyration, it matches perfectly with our actual radius. So in simple terms, the radius of gyration, it tells us the single distance where our mass or area could be concentrated to give us the same inertia as the real distributed shape. So I hope this clears things up, and if this helps, or if you'd like to see me build on this topic, please let me know in the comments section and I'll definitely do that. And until next time, I will see you in the next video.